All right, so welcome back once again. Now we are continuing from where we left off. This is lab week 4 activity. Now we are doing double indicator titration. And then this one, we are focusing on a mixture of sodium bicarbonate and sodium carbonate. Good. So now we are saying that the name actually is double indicator. So the basic thing you should know about this is that we are employing two different indicators. And then we'll talk about the two indicators as we go along, right? But now we are saying that this method is employed in the analysis of polyacidic bases or polybasic acids, of polyacidic bases or polybasic acid. Right now we are saying that we can use it to assay a mixture. Example is sodium hydroxide against sodium carbonate, a mixture of sodium bicarbonate and sodium carbonate, or potassium hydroxide and sodium carbonate, right? Good. Now we are saying that we employ the use of two indicators in a continuous process. And so one indicator is used, then the next indicator is added, and the process is continued till we get to the second endpoint. Good. Now we are seeing that for a mixture of bicarbonate, which has a pH of 8.3, and a carbonate which has a pH of 11.6, the reaction of the sodium carbonate with standard HCl occurs in two steps. Now the first step is that when I add this, because this has the higher alkalinity, right? It first of all starts the reaction with HCl, right? Now it will react partially, or not reacts partially, reacts fully, but then it reacts just to convert the carbonate to bicarbonate. And so you see there's a conversion of sodium carbonate, sodium bicarbonate, and then we also form sodium chloride. So this is the first. And then the indicator we use for this first step here is phenolphthalein. We are using it because it works within the pH of 10.0 to 8.2, right? Now, you realize that the pH of this one is 11.6. And so as we are converting all of these, to bicarbonate, then the pH is reducing gradually. It's reducing to the 8.3, right? And downwards. Now, once it's reducing, it can change within this, right? It can change the color of the phenolphthalein. And so you realize that when the color of the phenolphthalein changes, then we have gotten to the phenolphthalein end point. Right. Now, right after getting to the phenolphthalein endpoint, it means there's no carbonates in the medium. All the carbonates are converted to what? Bicarbonate. So at the phenolphthalein endpoint, you realize that the carbonate is mobbed up and then it's converted to what? Bicarbonate. Now, the next step, we have the bicarbonate reacting with the HCl, and then that will complete the reaction to give me sodium chloride plus water plus carbon dioxide. And then we use methyl orange for the second step because methyl orange changes pH within this range. It changes pH within this range. This is the acidic range. Now the resulting solution here will be acidic because the carbon dioxide can somehow dissolve in the water and produce carbonic acid. Right? Good. That is why we use that's why we use methyl orange, which changes color in the acidic medium, right? Good. Now, there's a sample question for us to solve. We'll use this question to understand the process better. Now, this is a whole new experiment we are doing, but then always the thing is that before we use any equipment in chemistry laboratory, we do calibration of the equipment, right? Before we use any solution, we do what? We do standardization of the solution. So these are the two things that we do. Now, we are not doing calibration here, but definitely we are doing standardization of the reagent, right? Now, we are saying that Kofi prepared approximately 0.3 molar HCl, standardize it with primary standard solution of annular sodium bicarbonate, right? Now, this is not the formula of sodium bicarbonate, so check it. This is not the formula of sodium bicarbonate, it's the formula of sodium carbonate instead. Now, the process was carried out in 3 kits, and then the average titer was given. In the lab manual, this wasn't what happened. They gave you the table for the standardization. So you go through everything that standardization requires. But then in this one, it has been simplified. We have given you the average titer already. Now we are seeing that we then acid a mixture of 5 liter sodium carbonate and sodium bicarbonate. Now we use 85 grams of sodium carbonate, we use 68 grams of sodium bicarbonate to make the mixture, right? And then we pipetted just 25 mils of the aliquot, right? 25 mils of the 5 liters in the conical flask. We added a few drops of phenolphthalein, did our titration with the 0.3 molar HCl, had our first endpoint. This is the table for the first endpoint. Then we added a few drops of methyl orange at the first endpoint, and then we continued the titration, right? The titration was continued with the HCl to go to the second endpoint. So this is the second endpoint. Then we said we repeated the experiment 3 times. So we have 3 different readings, right? Good. Now the questions. We are supposed to find the factor and the molarity of the carbonate solution used as primary standard. Now, the factor of this one, we've done it already, is equal to the actual, that's the actual weight you measured over the expected weight from the equivalent calculation you did. Then the molarity will be equal to the concentration, right? That is the expected over the nominal. I said it is the same as the concentration, which is equal to the concentration of the acid being standardized. So we are talking about 0.3 molar times the factor that we got from the first instance. Now, how am I getting the 0.3? The acid we are standardizing is 0.3. Always remember that the concentration of the standard or the primary standard is equal to the concentration of the solution being standardized. Good. Now we do that and then we answer our first 2 questions. The second one, the factor of the HCl, that's C1, V1, F1 is equal to C2, V2, F2. You can make F2 the subject and then find the factor. Then the actual concentration will be 0.3 times the factor, the F2. Very simple, right? So we are done with the first 2 ones. The next one that pertains particularly to the experiment we are doing today, the actual weight of the bicarbonate in the reaction, right? Now we'll go through how to find the actual weight of the bicarbonate, but then the idea behind this is that at the phenolphthalein endpoint, the bicarbonate is converted, right? The carbonate here is converted to what? Bicarbonate. Now you realize that this is not the final product we are expecting, so we cannot stop there. By literature, we know that if 3 mils reacted of the acid reacted to produce the first endpoint or to result in the first endpoint, now you require another 3 mils to convert this completely to the final product. And so what we do is that any value we have for the phenolphthalein endpoint, we multiply it by 2. So assuming the average titer was 3, we multiply it by 2, and then we get 6. That 6 mils of the HCl will be the total volume of HCl that reacted with all the bicarbonate in the medium. That reacted with all the bicarbonate completely in the medium, right? Now, once we get that mil, what we do is that we do milli equivalent in all we have talked about. This is the first time we are doing milli equivalent. So if you heard me say milli equivalent somewhere, no. Milli equivalent requires us to step down the volume compulsorily to 1 mil. Compulsorily to 1 mil. That is milli equivalent calculation. Do you get it? Good. And so what we do is that we write a general statement that maybe the mass of the carbonate in 1000 mil will be 1 molar HCl, right? Good. Now the whole ratio in this experiment is just 1:1. The first equation. This is the equation for the phenolphthalein endpoint, 1:1. So times 1 times 1, the same thing, right? Now I'll have to step down this one to 0.3 because that was given in the question. Then compulsorily, I'll step this one to at 1 mil. Usually we don't take it to 1 mil straight up. You take it to 100 and you can take it to 1 mil directly, right? That's what we do. Good. Now, at the methyl orange endpoint, everything has been reacted with, right? Assuming the total volume was 7. For us to know the amount of HCl that reacted with just the bicarbonate present, it will be 7 minus the phenolphthalein endpoint. So the 7 minus the 3, that will be 4. It means 4 mole of the HCl reacted with what? Reacted with just the bicarbonate in the medium. And then we can also extrapolate by doing milli equivalent calculations, correcting the mass using the assay values if given, right? And then doing other extrapolations. Very simple. Now, another thing you have to note here is that before, I've said it already, before you use the average titer in any calculation, what do? Multiply by a factor. Let's go through the calculation. Good. So we found the average titer for the phenolphthalein endpoint, the 3 divided by the 3 different values, the sum of them divided by 3. We found the average for the methyl-orange endpoint, right? Good. Now we are saying that the actual volume of HCl required to neutralize this will be 2 times the phenolphthalein endpoint, right? Good. And then we'll multiply that by the factor to get the actual volume. Now, the volume of the HCl that neutralized just the bicarbonate is the methyl-orange endpoint minus the phenolphthalein endpoint. And then for us to get the actual one, or for us to correct it, we multiply by the factor of HCl, right? Good. So we take note of these formulas. Let's start. Now, this is the equation at the phenolphthalein endpoint. The mole ratio is 1:1. We have to state it clearly. Now, we are doing milli equivalent calculation because we are stepping down to 1 ml. So milli equivalent 1 ml. Now, this is the mass of sodium carbonate, right? And then in 1,000 ml, we have 1 molar HCl. Now, we have to step this down to 0.3. So multiply it by 0.3, multiply this by 0.3, you get 31.8, right? Then the volume has to be stepped down to 1 ml. We don't step it down directly, so we step to 100 ml and then we step to 1 ml finally. Now, this is the statement that is most important to us. Very important. Now, what's the meaning of this statement? We are saying that if we have acid of this concentration, 1 ml of this acid reacts with this mass of the bicarbonate, reacts with 0.0318 grams. So we are saying that this means every ml of HCl released from the breath completely neutralizes 0.0318 grams of sodium carbonate in the pipetted volume of the mixture in the conical flask. That is the meaning of the statement. It means 1 ml of the acid will react with this mass of the carbonate. Good. Now, we have to do something, right? Good. Now, if the 1 ml of the acid reacts with this mass, right, then the average titer will react with what? Now, we are not using this average titer. We are using the corrected one, that is 2 times the phenolphthalein endpoint, right? Because this one will give us the total HCl that reacted with all the NaOH. Sorry, Na2CO3. That reacted with all the Na2CO3. And then this is correcting it. So we take this volume, right? Good. So we have 2 times the 5.2, that's the average titer, multiplied by the factor, that will be 12.94. Then we are saying that if 1 ml reacts with this from the milli equivalent, then 12.94 mLs will react with what? Then we do our calculations. So we'll do cross multiplication here. They will come and get 0.4115 grams. Now, this one gotten here is the mass of the bicarbonate that reacted with the acid that we had, right? Good. Now, we realize that we pipetted 25 mLs. And so it means that this mass is just present in 25 mLs. And so if this corresponds to 25 mLs, right, the 5 liters in the question had 5 liters, right? The 5 liters in the question, that is the 5,000 mLs, will contain what? So we scale it up and then we get to know that it will contain 82.3000 grams of sodium carbonate, right? Good. Now, we are saying that we have to find the molarity. The molarity can be found in so many different ways. This is one method I will explain. The other method is that we have C is equal to N over V, which is equal to M over molar mass times V. Now, this M here is the mass in grams. The volume here is the volume in dm cubes or liters, right? And then the molar mass here is in gram per mole. So if you can convert all these, you can just find your concentration speed up. If you find it difficult converting all these, then you might want to say that if 5,000 ml contains this one as calculated here, 100,000 ml will contain what? Right? So you just get the mass. And then once you get the mass in 1,000 ml, you can divide by what? The molar mass to get this, right? Now, this one directly will just give you the mass density. It will just give you the mass density. And so you can just actually use this formula. You can actually use this formula. So if I'm using the formula, the C is equal to M over M times V. Then I'll have, what's the mass? The mass is 82.3, right? All over. Now, what is the molar mass? The molar mass of carbonate is 106 times the volume. What is the volume? The volume in liters will be just 5 liters, right? Good. So let me punch this in my calculator and see. Okay, so I'm getting 0.155 molar. Now, you know, this is different from this. And then the idea is that there's a problem with this one because what we have found here is not the molarity, it is the mass density. It is the mass. So take note, this is the mass density. So the unit here cannot be molar. It just can be what? Gram per dm3. That is the formula for mass density, gram slash dm3 or gram per dm3, like this, right? This is it. Good. So if we want to actually find the molarity, then molarity is equal to, right? The mass density is equal to MC. That's P is equal to MC. That is, the mass density is equal to the molar mass times concentration. Then we can say that the molar mass is equal to the P over C. Oh, sorry. I want to make C the subject instead. So let me clean this. Now C, the concentration will be equal to the P over M, right? So I have to divide this 16.46 by, divided by the molar mass, that's 106. And that will give me this concentration accurately. So be careful when you are using your slides. I don't know if the corrections have been made, but then this is not the correct answer. This is the correct answer. Good. Now, yes, the next question was for us to find the percentage concentration. Now, the percentage concentration will be the percentage weight in volume. I've explained this one already. This is the grams, right? Grams in 100 ml of the solution. Good. And so what we do is that we just scale it down to 100 ml. So we are saying that 5,000 ml contain 82.3. 100 ml will contain what? Now we do our cross multiplication. We get 1.65 percentage weight in volume. Now this one means that we have 1.65 grams of the carbonate in 100 ml of the solution. Very simple. The last one is the percentage content. The percentage content is the actual weight in the measure as determined here, right, in the 5 liters over the expected. The expected was used in the experiment. So you realize that they weigh 85 grams of the carbonate, right? So that's the expected times 100. And that will produce as the percentage. Good. Now, all we have done would just be for the for the phenolphthalein endpoint or the first endpoint. Now, let's go to the metallurene endpoint. What equation is happening at the metallurene endpoint? The sodium bicarbonate is reacting with the hydrochloric acid to produce sodium chloride, carbon dioxide, and water. The mole ratio is 1:1, right? Good. And then, yes. Good. So we give the general statement for the standard, right? That's 84.000 grams of the bicarbonate, which is the molar mass, right? In 1,000 ml react with 1 molar HCl. Now we have to correct this with the mole ratio. So it's like this 1 times 1, this times 1, and then you bear with me that it doesn't really make any difference. The next one is that we step this one down to 0.3 molar. Now you can multiply this by 0.3. You multiply this one by 0.3, right? Then you have to step the volume down compulsorily to 1 ml. So we first step it down to 100 ml, and then you come to 1 ml. Very simple. Good. Then we are saying that per this statement, it means that if you have this concentration of the acid, right, 1 ml of it will react with 0.0252 grams of the bicarbonate, right? So that is the statement. That is the statement. But then who knows? Who knows the actual HCl that reacts? Now, I said that you can get the actual HCl that reacted with just the bicarbonate by subtracting the titer of the methyl orange endpoint, right? So you take the methyl orange endpoint and then you subtract the phenolphthalein from it. So that's what we have here, right? That's what we have here. We have the 16, which is this one, minus 5.20. So that's what we have here. That's what has been done here. And for us to find the actual, we always have to multiply by the factor, right? By the factor. Good. Now, we can say that if 1 ml from the milli equivalent, if 1 ml of the HCl reacts with this, then the 13.43, which has been gotten after multiplying by the factor, is reacting with how much? So yes, we get 0. We do cross multiplication here. We get 0.33484 grams of this. Now you realize that this one would be present in the 25 ml. That's the 25 ml aliquots that was used as the analyte, right? Now, if 25 ml contain this, then the 5,000 milliliters will contain how much? Remember in the question, the total volume given was 5 liters. That is the same as the 5,000 milliliters, right? Good. So you do your cross multiplication here, and then you get 67.68 of the bicarbonate. All right, so we do, and then we get this, right, 67.6800 grams of the bicarbonate. Good. Now, this will be the actual weight of the bicarbonate in the mixture. Good. Now we have to find molarity. Now, once again, as I corrected in the previous one, this is not molarity. What we get here is the mass density. And so if you want to get a molarity, you have to divide by the molar mass. You have to divide this by the molar mass, right? Now, how do we divide this by? What's the molar mass of this? It's 84. So it means you have to divide this by 84 to get it, right? If you don't want to confuse yourself, then you can just use the idea that the concentration is equal to the mass in grams over the molar mass in gram per mole times the volume in liters or dmq. Liters is the same as dmq. So the concentration will be equal to the mass. The mass is 67.6800 all over the molar mass. What's the molar mass? 84 times the volume. The volume is 5 liters, so 5. Good. I'm not using 5,000 because the volume is supposed to be stated in either dm cube or liters. Now I'll do my calculation on my calculator, and then I'm getting I'm getting 0.C is equal to 0.161 molar. So this is the actual molarity. Now, if you divide this by 84, you are supposed to get the same thing. If you divide it by 84, you are supposed to get the same thing. All right, so confirm you are getting the same thing. Good. Now the next one is for us to find the percentage concentration. The percentage concentration will be the mass in 100 mils. So if 5,000 contain this, right? 100 will contain, we'll do cross multiplication, we get 1.35 percentage weight in volume. This one means that we have 1.35 grams in 100 mils of the solution, right? Good. Now, we are saying that we have to find the percentage content, right? The percentage content, and then that is equal to the actual weight in the mixture as gotten from the experiment, right? All over the one that was weighed, the expected that was weighed. And so in this case, the expected is the one that we weighed. It's not like the other one where the expected was the one we got in the calculation. No. What we arrive from manipulating the titer value and getting from the calculation is the actual one present. The one that we weighed becomes the expected one. The one that we weighed becomes the expected one. So from the question, we realize that they weighed 68 grams, right? So that is the expected. And then the actual one was 67.68. So it's 67.68 divided by 68 times 100. That's giving us a 99.6% content, right? Good. Now the mole ratio will be the ratio of the two concentrations found, right? And then you get 1.2:1. Very simple. But now this is an exercise for us to try. The exercise is quite different because the acid we are using here is not HCl, even though in exams, what will come is highly HCl. It's possible with HCl. Now we are giving you what? Sulfuric acid. The equations have been written here so that your work becomes very easy. It is the same concept. Just pay attention to what? Your mole ratios when you are doing your milli equivalent calculation, and then you should be fine. You should try this and then throw it to any TA demonstrator or any member of the academic board, and then they can help you. Thank you very much for your audience.